Let's dive right into this explainer and set the stage for a seriously mind-bending journey into the physics of our universe. Today, we're going to explore one of the most famous and honestly often misunderstood scientific breakthroughs in human history, Albert Einstein's special theory of relativity. We're going to break this down step by step, moving from everyday intuition right up to the literal fabric of space and time.
So, is time the same for everyone? Well, I want to hook you immediately by challenging a fundamental assumption you probably hold. You see, we all go through life experiencing time as this constant, unyielding force, right? You can't see it, you can't hear it, but a second feels like a second, no matter where you are or what you're doing. We just naturally assume that a clock ticking in your room is ticking at the exact same rate as a clock on the other side of the planet or even out in deep space.
And for the longest time, thanks to the brilliant Isaac Newton, physics operated on that exact assumption. Time was absolute and moved unflinchingly in a single direction, kind of like a universal metronome. But, as we'll see today, Einstein completely shattered that rigid rule. He noted that the whole piece of time is a landscape and we move through it slice by slice. He realized time isn't a fixed backdrop at all. It's a landscape, and how you move through it fundamentally changes how you experience it.
Section 1. The illusion of motion. Why everything is relative. Okay, to understand how time and change, we first have to talk about motion. And the absolutely crucial point here is that motion is, in a way, an illusion. Or rather, it depends entirely on who is watching. This brings us to a foundational concept in physics called the frame of reference. Imagine it as the coordinate system you use to measure the world around you. If you're sitting in a room, that room is your frame of reference. Physicists divide these into two types: non-inertial frames, which are speeding up or turning, and inertial frames, which are perfectly at rest or moving at a constant uniform speed. Special relativity, as the name implies, deals specifically with those smooth, non-accelerating inertial frames.
Let's make this concrete. Imagine you're on a super smooth bullet train with no windows. You look at the person sitting next to you. In your frame of reference, they're completely at rest. Their speed is 0. But let's say I'm standing outside on the station platform, watching your train go by at 300 kilometers per hour. In my frame of reference, both you and that passenger are zooming past me at 300 kilometers per hour. So, who's right? Are you moving or are you at rest? The answer is both of you are right. Velocities are never absolute. They're always relative to the observer.
Section 2. The speed of light paradox, breaking the rules of motion. Now, let's see how this builds into a massive problem for physicists back in the early 20th century. Because while everyday objects follow these relative rules of motion, there is an ultimate rule breaker in the universe, and that is light. Thanks to James Clerk Maxwell's laws of electromagnetism, it was discovered that the speed of an electromagnetic wave, like light, is fixed at a staggering 300 million meters per second in a vacuum. It's an absolute constant, typically represented by the letter c.
But here is where we hit a massive, massive paradox. Imagine a hypothetical train moving toward you at half the speed of light. Now imagine that train suddenly turns on its headlights. Common sense and Isaac Newton's laws of motion tell us that you just add them up, right? The speed of that light should be the speed of the train plus the normal speed of light. To you on the platform, it should look like it's traveling at 1.5 times the speed of light.
But experiments actually proved that isn't true at all. No matter how fast the source of light is moving or how fast you are moving toward or away from it, light always hits you at exactly 300 million meters per second. This was a daunting dilemma for Einstein. You literally have Newton's laws saying velocities are relative and always add up, directly clashing with Maxwell's laws saying light speed is a fixed constant for everyone. These two giants of physics were completely contradicting each other.
Section 3. Einstein's two ground rules, the postulates of special relativity.
So Einstein realized he had to make a choice, and during a thought experiment on a tram car in Bern, Switzerland, he figured out a way to resolve this contradiction. He essentially laid down two new ground rules for how the universe operates. First, the principle of relativity. The laws of physics are identical in all non-accelerating inertial reference frames. Whether you're standing still or on a smooth-moving train, the rules of reality apply exactly the same way. Second, and this is the game changer, the speed of light in a vacuum is absolute. It is exactly the same for all observers, regardless of how fast they or the light source are moving. It never speeds up and it never slows down.
Section 4. Time dilation. Time slows down when speed stretches seconds.
Think about this. If the speed of light absolutely cannot change, something else has to give, right? Distance and time themselves must be flexible. Let's walk through the famous light clock thought experiment to visualize this.
Imagine a clock made of two parallel mirrors, with a single particle of light, a photon, bouncing straight up and down between them. Every time it hits a mirror, that's one tick. If you are on a stationary train with this clock, standing perfectly still relative to it, you just see the light going straight up and straight down.
But now, let's say that train zooms past the platform at an incredible speed. To you, on the train, the light still travels straight up and down. Let's just say it's covering a distance of 10 meters. But for an observer standing outside on the platform, watching the train go by, the mirror has actually moved forward while the light was traveling. So from the platform's perspective, the light didn't travel straight up and down at all. It traveled in a much longer diagonal path to catch up with the moving mirror.
Here is where the math kicks in, beautifully solving the paradox. The observer on the platform sees the light travel a longer diagonal distance. But remember Einstein's cardinal rule: the speed of light is constant. It cannot travel faster to cover that longer distance. If it travels a longer distance at the exact same speed, it literally must have taken more time. Time actually slowed down for the moving train from the perspective of the stationary platform. Physicists calculate this stretch using a mathematical term called the Lorentz factor, or gamma. The closer you move to the speed of light, the more time dilates. Clocks in motion truly tick slower than clocks at rest.
And because time is malleable like this, there is no such thing as universal simultaneity. Imagine lightning strikes both the front and the back of that fast-moving train. If you are standing in the exact middle of the platform, you see both strikes at the exact same time. But a passenger riding on the train is moving toward the light from the front strike and away from the light of the back strike. Because light speed is a fixed constant, the light from the front reaches them first. To the person on the train, the strikes absolutely did not happen simultaneously. And here's the wild part. Both perspectives are completely mathematically correct within their own frame of reference.
Section 5. Length contraction. Space shrinks. How motion compresses distance.
Okay, so time stretches for a moving observer. But remember, space and time compensate together to keep the speed of light constant. This brings us to the flip side, length contraction. If an object is moving relative to you, its physical length actually shrinks in the direction of its motion. Let's say we measure our train while it's resting at the station, and it's exactly 100 meters long. If that train zooms past you on the platform at half the speed of light, and you somehow measure it as it whizzes by, it won't be 100 meters long anymore. From the platform, that moving train physically contracts to just 86.6 meters long. It's not an optical illusion, guys. Physical space literally shrinks to maintain the constancy of the speed of light.
Section 6. The space-time connection. Merging dimensions.
All of this points to a monumental shift in how we view reality. We don't live in a 3D world with a ticking universal clock in the background. We actually live in a four-dimensional continuum called space-time. Whenever you describe an event, you need all four dimensions to accurately capture it. And this isn't just about high-speed trains. This distortion of space-time affects everything. It affects the mass of objects, the energy they hold, and it even explains gravity. Massive objects like the Earth literally warp this four-dimensional space-time fabric, and the closer you are to a massive object, the stronger the distortion and the slower time passes.
Which brings us to a final, rather provocative thought to close out this explainer. Time dilation affects everything, right down to basic biological processes. Earth's gravity is slightly stronger the closer you get to its center. That means time passes infinitesimally slower at your feet than it does up at your head. So, is your head actually slightly older than your feet? Yep, it absolutely is. We're talking fractions of nanoseconds for sure, but Einstein's math guarantees it. The universe is a far stranger, far more flexible place than our everyday common sense would ever have us believe. It's absolutely fascinating. I hope this gave you a solid grasp of special relativity and leaves you wondering just how time is flowing for you right in this very moment.